So spanning a space means, so let me move that important stuff right up. Okay, so vectors, let me call them, say, V1 up to, I'll use some different letters, say VL, span a space, a subspace, or just a vector space, I could say. Span a space means the space consists of all combinations of those vectors. That's exactly what we did with the column space. So now I could say in shorthand, the columns of a matrix span the column space. So remember, it's a bunch of vectors that have this property that they span a space. And actually, if I give you a bunch of vectors and say, okay, let S be the space that they span, in other words, let S contain all their combinations, that space S will be the smallest space with those vectors in it, right? Because any space with those vectors in it must have all the combinations of those vectors in it. And if I stop there, then I've got the smallest space, and that's the space that they span. Okay, so I'm just, rather than needing to say, take all linear combinations and put them in a space, I'm compressing that into the word span. Straightforward. Okay. So if I think of the column space of a matrix, so I start with the columns. I take all their combinations. That gives me the column space. They span the column space. Now, are they independent? Maybe yes, maybe no. It depends on the particular columns that went into that matrix. But obviously, I'm highly interested in a set of vectors that spans the space and is independent. That means like I've got the right number of vectors. If I didn't have all of them, I wouldn't have my whole space. If I